Hello. So now in this class, we'll be continuing with the topic, the mechanical behavior of bone. Okay. And last Friday, we have discussed about it. But since there was a gap between the last class and today's class, I will try to quickly go through some of the highlights of our discussion and then move on from where we had left in the last class. Now, bone structure and the mechanical properties are very important constituent of this course. And as I have already discussed, bone is primarily composed of collagen fibers and small crystals of inorganic bone mineral, hydrated calcium hydroxyapatite. Okay, it has an organic part, which is the collagen fiber, and an inorganic part, which is the hydrated calcium hydroxyapatite. The role of the hydroxyapatite is to contribute towards the stiffness of the bone generally, while the collagen content actually determines the ductility. Okay. Now, primarily, you will see that bone exists as a matrix of solid mineralized tissue as well as fluid part. Okay, and that is the reason we have generally quantified the mechanical property starting from the density, not as pure density, but as an apparent density. We will discuss this a little later. But from molecular perspective, bone mimics a true composite material. It consists of 65% minerals, that is hydroxyapatite, and 35% of organic collagen fiber. Okay, as I told you, collagen fiber are actually organic matrix, and the inorganic bone mineral is inorganic part is the bone mineral hydrated calcium hydroxide. Now, if you look into the bone structure, as you can see here, that there is spongy bone inside. It forms the core of the bone structure and covered by very hard, dense cortical layer or compact bone. If you zoom into it, you can see it more clearly here that there are pores inside the spongy structure. This is known as spongy bone, popularly as cancellous bone, also known as trabecular bone. And if you take one small sample, we call it a trabecule. Okay. Now, apart from the solid mineralized bone tissue, you have bone marrow, as you can see, water, fat, and also you see the blood vessels, the red blood vessels, which actually carries the nutrients, and the bone is richly supplied with blood vessels to keep it alive. Now we classify bone tissue based on porosity. This is very, very important. How do we classify bone? Okay, based on porosity or density. So compact bone is a dense solid, as you can see here, in the picture. So it is a dense, solid bone, and which contains actually more than 70% volume fraction of solid. Okay. Whereas cancellous or trabecular bone is a porous network of connecting rods, plates with volume fraction of solids less than 70%. So if you take a volume of bone and then calculate the volume fraction of solid mineralized tissue in that sample, then anything greater than 70% belongs to the compact bone. Anything less than 70% belongs to cancellous bone. Okay, this is very clearly visible if we have a mid-frontal section cut through a femur sample, proximal femur. Okay, the proximal part of the femur consists very clearly of an inner core of porous network of cancellous bone covered by the dense, solid, compact or cortical bone, thereby resembling a sandwich construction. Now, just more sort of explanation in form of figures. You can see very clearly how does this bone structure look like. Okay, so this is the trabecular or spongy bone. This is the epiphysis part of the femur. So this, and if you move towards the shaft of the femur, it's the diaphysis part. So as you know already, epiphysis is the area where it's the articulating zone. It actually meets other bones and form the joints. So obviously the femur head is covered by articular cartilage. There is cartilage also towards the trochanteric region. But as you can see from the picture, very clearly you have a medullary cavity, intermedullary cavity that contains marrow. And what is noticeable is the cancellous bone structure is more towards the epiphysis of the femur bone. As you move towards the shaft, it is more dominated by thick, solid cortical bone. Inside the medullary cavity, you have the bone marrow. Okay. So if you go on magnifying, and magnifying, you will see, more inner structure of the cancellous bone, which is basically a network of rods and plates. And inside you have canals, you have blood supply. So this, in a way, is a very complex structure that supports your body weight and different kinds of forces that the skeleton is actually subject to during different kinds of physiologic movement. Now let us move into the bone structure. The compact bone tissue forms the structural shell of most bones and nearly all of the diaphysis of long bones. Okay, the femur is a long bone, tibia is a long bone, so the diaphysis part is mostly made up of compact bone. The cancellous bone forms the inner core and is a cellular material. Very important, it's a cellular material made up of network of rods and plates. So these figures below the slides is trying to explain the different structures of cancellous bone, which is made up of network of rods and plates. So a network of rods, of course, when it is a network of rods, the porosity increases, the density decreases. So it is more an open cell structure, whereas when it is converted towards plate-like structures, so it gives you a more closed cell structure. Of course, in case of the network of plates, the porosity decreases, thereby the density increases. So more material is accumulating in the cell walls, giving it a more closed cell structure. Now, the mechanical behavior of cancellous bone is similar to cellular material. What is an example of a cellular material is polymeric foam. Okay. So the mechanics, obviously, for a cellular material is distinctly different from that of a solid material. Now, how do we measure bone mineralized tissue? Because we as engineers and scientists, we need to quantify things. The clinical world is a bit different from what we try to do. So we first need to quantify bone mineralized tissue. Now, as I told you earlier, that bone exists as a two-phase porous material. We have a solid phase, which is composed of bone mineralized tissue, and a fluid phase, which is composed of blood vessels, blood, marrow, and interterrestrial fluid. Okay? The apparent density is a very important measurement that characterizes bone mineralized tissue. The first thing that is used to mechanically characterize bone mineralized tissue. So it is the mineralized tissue per total volume of the tissue. If you take a sample, say 1 millimeter cube from any, say, bone structure, then that 1 millimeter cube consists of a solid part and a fluid part. Okay, because it has pores, and the pores contains the fluid part, and of course it has a solid part. Now, if we clean it and measure the weight, you know how to measure the volume of that particular sample. And if we divide the weight by the volume, we actually don't get an actual density measurement, but we get what is called the apparent density. That's the reason it is apparent, because it is a porous structure. Okay, so on the one hand, when we are measuring volume, we are considering solid plus fluid, but when we are measuring the weight, we are actually measuring only the solid part of the bone mineralized tissue. Okay, and then when we are calculating it, we are calculating actually an apparent density, not a real density. I hope you understand the difference. Now, there have been other attempts to quantify or measure the bone mineralized tissue. Ash density is a measurement, and ash density is the ash weight per total tissue volume. Then there came a relative density, which is defined as the density of the cellular solid divided by the density of the solid it is made from. Now, this relative density is analogous or equivalent to volume fraction of solids. Okay, at low relative densities, it has rods connecting to form open cell. I have already discussed. At higher relative densities, more material is accumulated in the cell walls, and the structure transforms from into a more closed network of plates. So from open cell structure, rod-like open cell network structure, to a more closed cell network structure is the transformation from a low relative density to a higher relative density. Now, if we try to look into the stress strain curve that we are very much interested, it's very interesting to know the difference in the behavior in the two types of bone. One is the cancellous bone. This is the spongy network of bone, and another is the solid structural shell, which is the compact bone. Let us first pay attention towards the cancellous bone stress strain curve. You can see at 3 different relative densities, we have 3 different curves. Okay. Now, as the relative density is increasing, I hope you can clearly see that from 0.3, 0.4 to 0.5. The whole stress strain curve is becoming more steeper. Okay? And a very important thing here, that at very low relative density, 0.3, for the case of 0.3 and 0.4, you see an appreciable plastic deformation phase, okay, which is followed by a steep rise in the stress strain curve, both for 0.3 and 0.4. So some transformation in structure is happening in this zone. Whereas for 0.5, you can see this portion is comparatively much less as compared to these 2 cases. But the rise in the structure, there is a dip and then there is a rise. Here in these 2 cases, 0.3 and 0.4, it's almost flat. And then there is followed by a rise in the stress strain curve. So some structural change is happening for which there is an increase in the stiffness of the material. Okay. But if you just simply compare the 2 characteristic curves of cancellous bone and compact bone, you can immediately conclude that the cancellous bone is exhibiting a more ductile behavior, whereas the compact bone is exhibiting more brittle type of behavior. Okay. Now, some salient features of the stress strain curve are that the stress strain curve of the cancellous bone has 3 distinct phases of behavior. First phase is the behavior is linear elastic, and if you try to relate it with the structure, is we can relate it in such a way that the behavior is linear elastic as the cell walls basically bend and compress axially to the applied loading conditions. Okay, so cell walls are bending and compressing axially. Okay, in the phase 2, which is eventually at high load, the cells begin to collapse by elastic buckling, plastic yielding, or brittle fracture. This is a transformation phase. So the cell walls are changing its structures. They are collapsing by elastic buckling, plastic yielding, or brittle fracture of the cell walls. This second phase of the collapse progresses at a roughly constant load until the cell walls meet and touch. So the structure is changing. In the third phase, once this whole second phase is complete, the collapse process is complete, and the cell walls are meeting each other, it gives rise to a new structure. So once this whole process, phase 2, is complete, the resistance to the load increases, giving rise to a final increasing steep portion of the stress strain curve, which is clearly visible in the behavior of the cancellous bone as shown in the figure. Now, over the last few decades, there have been several attempts to quantify the behavior of cancellous bone. Now, within the few decades, there has been 2 major contributions, although there have been several papers. Okay, I have myself been trying to work with it because as mechanical engineers, you are very much interested about the Young's modulus value of a particular location of the cancellous bone. And you can easily understand that this Young's modulus and the apparent density, both starts from the apparent density. They are related to each other, and this apparent density will vary from one location to the other, giving it a heterogeneous characteristic of the cancellous bone. So this is very important because the Young's modulus of the bone structure of cancellous bone will vary from one point to the other. Now, there has been several attempts to quantify that until, there has been many equations that have come up, linear relationships, power law relationships, and have been suggested, trying to fit the models with the experimental data. But finally, the power law models have been well established, which is more of an empirical relationship. Now, as you can see that E is equal to or related to apparent density through a power law relationship where A and B are constant. Okay. Now, A is a constant and B is the exponent. But generally, E is related to rho, depending on the structure, depending on the location of the cancellous bone within a particular anatomic location. But a major contribution came up from Carter and Hayes in 1977. I will share this paper. I have a soft copy of this paper, so I'm going to post it today because you're all back from your spring break, so you would take time to concentrate, I hope. And I did not do it after the last class because I assume that you need a break after your examination. So I'm going to share Carter and Hayes' paper as well as the other paper that I had also discussed, the Gibson paper, Gibson 1985, published in Journal of Biomechanics. So what Carter and Hayes suggested is a relationship which has been widely used. It is E equal to 3790. This is the constant A. There is a term which contains the strain rate. He introduced strain rate. This is another property of the cancellous bone. We are keeping that aside for the moment, but rho is the apparent density to the power cube. Okay, basically it is rho cube. So we have an exponent of 3 and we have a constant of 3790. Now you can observe that E is expressed in MPa, megapascal, and rho is expressed in grams per centimeter cube. Okay. Now these two dimensionally doesn't match because one side you have MPa, the other side you have grams per cc. But remember, this is an empirical relationship. That's the reason we can write this equation based on experimental values, of course, backed up by theoretical knowledge. But essentially, this is an empirical relationship. Now, the strain rate is a term which I'm going to take up later. Basically, it is a property which is popularly in a material, it is popularly known as viscoelastic property of the material. Okay. Now, the specimens were taken from the human tibial plateau and bovine femoral condyles. Okay, so you have a mixture of human bone taken from the tibial plateau, and bovine is cow bone, femoral condyles, with different geometry, tested for varying strain rates. So the strain rate means the rate of loading at which you are applying the load. Okay, so it varied significantly from 0.001 to 10 per second. Okay, so this is a huge range. Okay, what was observed that the viscous flow of marrow influenced the trabecular bone only at a high strain rate. Okay, so the viscous flow of the marrow basically influences the trabecular bone property at a very high strain rate, that is 10 per second, which suggests that the presence of marrow during severe traumatic compressive loading in vivo may serve to absorb considerable energy. Okay, so the viscoelastic property, the spring dashpot system that is inbuilt in the bone structure, comes into play only during impact type of loading. Okay, only at a very high strain rate. Comparatively, the apparent density is a much more important factor than the strain rate. So at low to moderate strain rate, it has very little influence on the E modulus. But at a very high strain rate, say impact force, severe traumatic compressive loading, actually the spring dashpot system is activated and they can absorb a considerable amount of energy and offers resistance or more stiffness to the bone structure. Okay, so what was concluded that within these two variables, the strain rate and the apparent density is a much more important factor than the strain rate if we consider the human being's activity more in the low to moderate strain rate range. Okay, because we are mostly doing our physiological activity, which is a sort of a rate of loading in the low to moderate strain rate range. Now, as I told you, the next very important contribution towards characterizing mechanical behavior of cancellous bone came from L.J. Gibson. Okay, she is a civil engineer now working as professor in MIT. Actually, came up with more detailed explanation of these relationships and the relationships between the empirical. Basically, she tried to connect the theoretical or analytical models of bone structure and the empirical relationships of E and rho. So Gibson basically analysis, as you can see here, suggested two different powers or exponents, 2 and 3, for two different structures. One is the open cell structure, another is the closed cell structure. Okay, so let me just explain you first the figure that I have attached, then I will conclude with the text. So all the data, as you can see here, are data belong to Carter and Hayes. So here also you can see that the human tibial plateau and the bovine femoral condyles, different types of data plotted with different symbols. Now, what Gibson tried to do is to relate the behavior with the analytical models of the cancellous bone. The analytical models of the cancellous bone are the open cell behavior, as you can see here, and a closed cell behavior. And there is, of course, a transition phase. Now, what was concluded was both theoretically and experimentally, what Gibson tried to fit is the model with the experimental data of Carter and Hayes, and also little later, Michel Dalstra of Aarhus University in Denmark tested and tried to come up with relationships for the pelvic trabecular bone. So this relationship can vary slightly from one anatomic region to the other. So he came up with mechanical and textural properties of pelvic trabecular bone. And this is another paper that is quite often referred if you're working in the trabecular bone, pelvic region. So we need the relationship for different types of investigations related to structural behavior of the bone, pelvic bone. Now, it has been established that both theoretically and experimentally, that Young's modulus of the cancellous bone was strongly dependent on bone apparent density. So this is the first important conclusion over decades of research. And the power law model was better suited than the linear model for characterizing mechanical property of cancellous bone. So these two were the major conclusion, our years of rigorous study on the behavior of cancellous bone. Gibson analysis showed that the E varies from 2 to 3, okay? So it can be also 2 point something, it can be 3 point something. So roughly it varies, the exponents varies between 2 and 3. 2 is more resembling the open cell structure, whereas 3 is resembling more closed cell structure. So obviously, when you are transforming, when from the bone structure is transforming from open cell to closed cell structure, it is mainly due to accumulation of more bone mineralized tissue in the cell walls, okay, as I have discussed earlier. So results of Carter and Hayes, 1977, agreed with this prediction and suggested a transition, very important, suggested a transition from rod-like structure to plate-like structure at a density of around 350 kg per meter cube. So this is somewhere located here. The transition at about a point 350 kg per meter cube, or a relative density of 0.2. Okay, so this is basically log-log graph, and what has been found out that the transition takes place at a cutoff point of 350 kg per meter cube. Okay, from open cell to closed cell structure. Another very important or fascinating property of bone is that it's a highly adaptive material, and it is sensitive to the mechanical environment it is subject to. What is meant by mechanical environment? Of course, mechanical environment is influenced by the structure as well as the loading. It is highly sensitive to loading, and it is, as it has been mentioned, in clinical terms, sensitive to DCUs. So if you are not if using your bone structure to perform different physiological activities, you are disusing it. And of course, if you are immobilized, so the bone cells are not receiving enough mechanical stimulus due to immobilization, due to structural intervention, and due to vigorous activity at high loads. That means you are giving, if it is a case of vigorous activity at high loads, you are giving too much of mechanical stimulus. And if there is a structural intervention, then of course you are including some components, foreign materials, which influences the mechanical environment within the bone structure and thereby influences the adaptive property of the bone. So bone tissue may change its properties in response to changes in mechanical environment. This is a very important conclusion. Okay, so this property was first concluded by the German scientist, anatomist, and it is named after him, named as the Wolff's law, which says that each change in the form and function of bone or its function is followed by a certain definitive changes in its internal architecture, okay, internal structure of the bone, and secondary changes equally definitive in its external compliance. So the bone not only changes its internal structure, it can also change its external compliance in according to some mathematical laws. So in a very summarized manner, we can say the cancellous bone structure is changed, which belongs to internal remodeling or internal bone structure. And when we talk about external compliance, we mean that the thickness of the cortical bone, the cortical layer, they can increase or decrease depending on the mechanical environment. Okay, so both things can happen. But generally speaking, when a person has reached adulthood, the change in external compliance is more prevalent in cases in the growing age, okay, between 10 to 18. Okay, so if you see that there is a definitive change in the external compliance, the geometry, the thickness of cortical layer, all these things are visible changes happen in human body during the growing period from a child to adult. So, but once you reach an adulthood, your bone structure reaches an equilibrium as far as the structural changes are concerned. Now, once it reaches that state of equilibrium, what happens is changes in internal bone structure. So changes in the cancellous bone structure due to changes in the mechanical environment. Okay, so this is exactly what happens, due to the fascinating property of bone to adapt its structure according to the changes in mechanical environment. So there has been a theory of adaptive bone remodeling, okay, which is based on some important assumptions. The process is regulated. The first thing that I would like to say is the process is regulated by mechanical stimulus detected by sensors within bone. Okay, so there are sensors within bone which can detect the mechanical stimulus. Integrated with hormonal, genetic, and metabolic factors, this actually causes bone apposition or resorption. So two things. Bone apposition means increase in bone density. Resorption means basically loss. So one is addition, one is loss. So if the bone density either increases or when bone density decreases due to activities of bone cells, osteoblasts and osteoclasts. I hope you people are conversant with the term osteoblast and osteoclast. It is basically two types of bone cells. Okay, so the activity of osteoblasts is to generate bone or increase in bone. This is responsible for bone density increase, whereas an osteoclast is more responsible for bone loss. Okay, so these two types of cells are responsible for apposition and resorption respectively. And this goes on continuously inside the human body. Okay, the activities of osteoblast or osteoblastic activity and osteoclastic activity is continuously going on inside the body. For a normal patient, this reaches always an equilibrium state. The rate of bone resorption is equal to the rate of bone apposition. So thereby, there is no net increase or decrease in the bone volume in the human body for a normal person. Okay, but with changes in mechanical environment, it basically triggers bone remodeling. Naturally loaded bone exists in a state of equilibrium, as I was explaining you. Normal loading and consequently a normal stimulus distribution leads to an equilibrium state with normal bone morphology. Okay, in which the amount of bone formation is balanced by the amount of bone resorption. I just explained you the rate of bone formation or amount of bone formation is equal to the amount of bone resorption. Thereby, there is no net change in the bone structure in a normal situation. An unnatural situation or unnatural loading actually alters the mechanical stimulus pattern, and adaptive bone remodeling leads to a new equilibrium state. So what happens if there is a change in the mechanical environment? Bone will adapt its structure and reattain a new equilibrium state. Okay, it will try to accommodate the change, and by adapting its structure, and it will reach again another new equilibrium state. So bone tissue, say for implanted bones, tries to normalize its stress strain pattern locally to the same value as the natural bone under the same loading condition. So take the case of a patient, say, take the case of a student who actually breaks his leg or breaks his arm doing some sports activity, and he goes to a doctor who puts some plates and screws to rejoin the fragmented part and let the bone heal. Immediately in that location, in the domain of inclusion of plates and screws, there would be some changes, visible changes in the bone structure. Okay, because earlier situation, unfractured situation, the whole load was being carried by the bone tissue itself. Now, in a fractured situation, a part of the load is being carried by the plates and screws. Thereby, there is a change in the stress distribution, whole in the domain of inclusion of the implant. This change is responsible, change in mechanical environment, then triggers some bone remodeling in the structure, and the bone actually tries to strive to reach the natural state by adapting its structure. But you don't know what will happen for the new equilibrium state. So that needs to be quantified. So all changes in the mechanical stimulus is generally expressed. This mechanical stimulus generally quantified as strain energy density levels between pre and post implantation. So strain energy density is an important variable that actually measures mechanical stimulus. So all changes in the mechanical stimulus are assumed to be caused by the implant itself and not by changes in the external load. So when we try to establish this theory in form of mathematical equation, we assume that intrusion of the implantation is solely responsible for changes in the mechanical environment, not by changes in external load. Because the same patient, say patient may be a student, patient may be an elderly person, a middle-aged person, he or she has been undergoing the same, daily loading cycles in form of physiological activities. So there's not much change in the loading condition it is subject to, the bone sample. But what is then responsible for this change in the mechanical stimulus? The change is mainly triggered by implantation. Okay, so this is an assumption. So this, in order to investigate the extent to which the mechanical stimulus is responsible for the bone adaptation, we actually consider the pre and post implantation. And we assume that all these mechanical changes is caused by the implant itself and not by any external load. Okay? So the effect of implantation triggers bone remodeling. This is summarized as implant change in mechanical environment, and which leads further to structural and morphological change in the bone. This is to summarize the whole property of bone adaptation. Can you hear me? Hello? Just a moment. Let me. Hello? Hello?
Yes, sir.
Yes, sir.